I'd like to tell you a bit about the work we've been doing in my group on verification of subsets of Rust. So Rust is as you know, a very big language, and we're just making some small steps to verify some subsets of Rust that are important to us. And I would like to emphasize that this is work with my postdocs and PhD students at the Cobra Center. So that's the Concordium blockchain center at Aarhus University. And I'll say a bit more about the center in a minute. I lost the focus of my mouse. Now it should work better. So this is a research center at Aarhus University, and we're making close collaboration with the. I have a setup where I cannot precisely see my screen. Just give me a minute. That should be better. My apologies for that. And we've been collaborating both with the Concordium company and with the Cobra Center in DevX, and we have the collaboration with the Rust Crypto Interest Group, and in dialogue with Survey. We also, had quite interesting discussions about the Rust Formal Methods Group. And I want to take the opportunity also to thank Survey for all the work he's putting into the Formal Methods Interest Group. I think it's going great. So why do we want to do formal verification, and in particular for the application to blockchain? So if you make a bug in the implementation of cryptography, then people can print money. And if you have an anonymous coin, then people can print an unlimited amount of money, and you will never know whether it happened, and there's no way to actually return that. So this is very important. And this is actually something that happened in practice. It's well documented. And bugs in smart contracts. So smart contracts are small programs running on top of a blockchain, allow people to steal tens of millions of dollars or euros, currency you like. And it might even be the case that these people actually are following the rules of the game. Because in one of these hacks, it was stated that code is law, and the interpretation of the smart contract should be precisely according to the letter of the rules of the smart contract. So if someone makes a programming bug, which actually happened, then if you abuse this, then you say, well, this was actually an intended. This was not a bug. This was a feature, and I've just been using the contract as it was stated. And this is happening more and more. So basically, each week, some smart contract loses tens of millions of dollars. So this is a good application for formal methods. So what do I mean by formal methods? We have unit tests, property-based testing. I'll say a bit about how we use property-based testing. We have some lightweight tools for formal methods, type checkers, model checking, static analysis. I'll say a bit more about the type checking we're using, and then formal verification, both automatic and interactive. So automatic tools can prove some properties of software, and Survey has trying to convince me that it can actually do an awful can do more and more, and he's been quite convincing in that respect. But still, if you want to do big programs, then you still need a computer to help you out, as most of you will know. And so we use a computer proof assistant, and the one we're using in my group, and I've been using for 2 decades now, I think, is the Coq proof assistant, and it's been used to prove correctness of compilers, a hypervisor, smart contracts, and it's the state of the art in programming language research. If you look at a conference like POPL, Principle of Programming Language, then about 20-30% of the papers actually comes with a formal proof, because no one actually wants to read your long, tedious appendix where you do an enormous induction proof, and papers are actually rejected there because, well, people basically didn't do their homework. So if you're looking at what's happening in programming language research, that's the kind of tool that you want to use. And so what do you prove? Things like functional correctness, properties of programming language like preservation of semantics, type safety. Now, what does this coq proof assistant look like? Most of you will know this, but I'll just want to make sure that everyone's on the same page. It has a functional programming language and then a logic and type theory. And actually, the logic and type theory are very much connected by the Curry-Howard correspondence. You use this logic and type theory for specifications. And I have a small illustration for you where you can see what the head and the tail of a list look like. And as you can see, this is just a perfectly ordinary functional language that looks very much like OCaml. Then the only difference is that now you use basically the same language to also write your specifications. So coq is a big system, but what's happening is that everything is reduced to a small logical kernel, and this kernel has been inspected by many people. And there's as always, there's if you write a new programming language, you want the programming language to compile itself. And there's a similar project going on in coq where it's called the MetaCoq project. And part of the goals is to actually prove coq to be correct in itself. Another very powerful feature of the coq proof assistant is that it has tens of thousands of users. And this really helps to make sure that there are big libraries and there's a very good community around it. There's a nice package manager and separate libraries and so on. So there's a very good community around the proof assistant. So here's a very biased state-of-the-art of formal verification in Rust, and this is just so that people can scream at me at the end of the talk. So unlike C, there's no precise semantics for Rust, and as we've heard, is that the Veracene project is one of the projects that actually tries to improve on this. If you look at WebAssembly, that is sort of a very good example of what you would like a new language to look like. So this has a very precise and formalized semantics and a proof of type safety in coq actually, and in both in coq and in Isabelle. Another project on the way of specifying Rust or verifying Rust is the Vellum project, which specifies part of the LLVM intermediate, or the LLVM framework. And then there's Rustbelt, which has a model of the MER intermediate language. But I would like to emphasize it's only a model. It cannot be used to verify any Rust programs. But it is a really good model which really helped to clarify many parts of the Rust language. And then there's the automatic tools. We already had a presentation about Frusty. There's Rusthorn and Crusoe, the tool by Xavier, that can do very impressive work. So a long-term goal, just like we have for the C language, would be to have a verified compiler for Rust, but that will take a couple of years. But any steps along those roads would already be very welcome. There's a long list of tools on our homepage for the formal methods in this group. So if your tool is missing there, please send us some elaboration or send a pull request and we can add it there. So as I said, so this is an enormous project, and there's lots of parts of Rust that haven't been specified. So we're going to make very small steps, and I'd like to start with sort of the simplest part, which is called hexspec, and I'll introduce that in a minute. And I want to talk about 3 projects here and some of our contributions to those. So hexspec is a stateful part of Rust with a pure semantics. Then there's Fiat Rust and Bedrock, which is a small imperative language with expressions that is used especially for cryptographic code. And then we're going to look at pure functional Rust for smart contracts. Hexpack, this is a tool developed by Denis Marigot, Franciscus Kiefer, and Kartik. And so that the name may sound a bit strange, but the idea is you have high assurance cryptography. High assurance cryptography means it's functionally correct, cryptographically secure, fast, and constant time. It's easy to, or it's already hard to get some of these, but the holy grail is to actually have all of them at the same time. And their big insight was that instead of writing your internet standards in pseudocode, you can actually use the Rust language to write your specification in, and then you can give this a semantics in a number of tools. What they've done is to actually provide a precise type checker and operational semantics and an embedding in EasyCrypt and F* proof assistants. So those are proof assistants, somewhat like the Coq proof assistant, but with a more niche market, if you want. EasyCrypt is specifically used for game helping proofs in cryptography, and F*, I think the main application is to write a clean slate implementation of the TLS protocol. So what we've done is to add a Coq backend to Hexpack, and this allows us to connect it up with the other project that I'm going to talk about. This wasn't too hard because already the F* and the EasyCrypt backends existed, and it's a variation on those. So there's a main advantage of this is that we can now actually prove the group laws for elliptic curves instead of just unit testing them. So this is a big difference from what you would get from if you look at the prototype implementations that come with an internet standard. And one of the things that was actually done by two of our bachelor students was to implement the BLS. So this is a pairing friendly elliptic curve. And this is currently being standardized. So they implemented this in the Hexpack language. And so now this means that we can translate this from Rust to Coq by combining those two things. And I'll say a bit more about this in a minute. Because I need another ingredient. So this is two frameworks, the Fiat framework and the Bedrock framework. So Fiat is a verified compiler or a verified compiler. You have a small sublanguage in the Coq system that is geared towards finite field operations. And what you can do is then using partial evaluation to actually make a very fast implementation, very fast platform independent and constant time implementation out of this. And you know that this is actually correct because the compiler was verified in Coq. Now, making sure that everything, so how do we make sure that everything is constant time? Because it's just straight line code. And so this is very nice, but that also means that there's part of your code you cannot directly implement in this small sublanguage. So what we needed to do was to add loops and function calls to this language. And we used another project from the same group. This is the group of Adam Chipala at MIT, which is the Bedrock system. And this has a number of goals. One is to actually generate very low-level code in RISC-V actually, and with the application of Internet of Things, IoT. So what we've done is to make, so what Bedrock provides is a very small C-like language embedded in Coq, but which is richer than what is provided by Fiat or fiat crypto. What we can now do is to print this language. So this already had a way of printing to C, and what we've added, this is mostly done by my PhD student Rasmus. He actually printed this to Rust. So now we can take the whole thing. There was already a Rust backend for the fiat cryptography compiler, not only a Rust backend, but also C, Go, and Java backends. So now we've combined this, the Rust backend for fiat crypto with the Rust backend for Bedrock, so that we can directly generate an implementation of BLS. And what I'm very happy to report is that, and this is collaboration with Rasmus and Benjamin, who Benjamin, he implemented very fast field inversion, and Diego Aranya, who's an expert. You probably know him from the Rust cryptography interest group. He's an expert on cryptographic implementations. So what we managed to do was actually to generate an implementation of BLS, and this is actually only twice as slow as the implementation that's written by hand. And we know we have a good idea of how to actually speed this up, but this hasn't been done yet. So not only is it, is it completely secure? It's generated, it's platform independent, but it's also efficient. So here's the whole pipeline. You start from a bit of pseudocode in your internet standard, then you translate this by hand into hexspec. So that's a fairly straightforward programming exercise. Then we can go from hexspec to one of its backends, and we choose Coq for this one. And then we use the fiat library to combine with Bedrock to actually generate Rust, but we could also generate C or Go. And we've done this for the BLS curve, part of the elliptic curve cryptography, to generate an efficient implementation. Now you can think, well, this is mostly a toy, this high assurance crypto, and it's a dream of academics, but it's actually used we're using it right now. The browser I'm using is the Brave browser. It's a variant of the Chrome browser, and that's actually running on fiat cryptography. The Firefox browser uses the Heckle library, which is a library written in F***, provided by the Everest project. The Wirecard VPN, which is used in the Linux kernel, it uses both these libraries, so both fiat crypto and the Heckle library. Our code that was written by Benjamin is running in the Mirage OS operating system. So this is an operating system written in OCaml. So all of these things are actually running in production. So this is not a toy. This is things that are actually that we're actually using in our daily lives. A bit more about how we actually did this. So what we do is we start from hexspec, then we compile to this functional specification. We write it, we write a faster implementation in Bedrock 2, and we write, so that's Bedrock 2 is mostly the glue code, but the fiat cryptography, it generates a very fast implementation of the finite field arithmetic. So from fiat, fiat has a C backend, but also has a Bedrock backend. So in Bedrock, we actually combine those two. Then we verify in Coq that this is actually correct with respect to the functional specification we got from hexspec. And then we print to save Rust. Of course, what you can see here is that there are two parts. So everything in the circle or in the ellipse is actually verified. The part from printing to save Rust hasn't been verified yet, and this is in part because there's no full semantics of full specification of Rust. So once a project like Rustbelt is more actually would treat something closer to actual Rust, we could try and verify this. Similarly, for hexspec, the soundness has not been proven from the operational semantics against the denotational semantics, but this is something that can be done and should be done at some point when someone has the time for this. So here's even a bit more where you can see both the G1 and the G2 groups. And you see a bit more of how this what this actually looks like. What we're using, so most of the verification in fiat crypto uses the standard logic of yes, that's correct. So most of the verification in fiat cryptography uses the standard logic of Coq. Bedrock uses so-called separation logic because it needs to deal with pointer arithmetic. And as I said, so this implementation is fast, but we know where the bottlenecks for performance are. So we're missing things like lazy reduction and comba SOS. So if we and these things are possible to add to a project like Fiat, but it's just something that we should do, and we should do very careful testing on where the bottlenecks are. But these things certainly seem to be in scope. We've implemented quite a big part of the BLS standards. What we're currently working on is hashing to curve to actually specify this in hexspec, and then we would like to implement it in Fiat Bedrock to make sure that we can actually generate more of the standard. Another thing we've done is to add property-based testing to hexspec, because if you look at what the internet standard looks like, you get a bunch of pseudocode, some reference implementations, and some unit tests. What you can do instead is to use property-based testing to actually test that, for example, if you do that the addition of two group elements again ends up in the on the curve. Another thing we've added is, and this is in the same line, we've added support for Crusoe. This is the tool by Xavier. This has a specification language, and he proposes this just to build up some of the suspense for his talk. So he proposes this as a specification language for Rust, as a general specification language for Rust, and we've added this to the hexspec language, so we can actually write more of the specification. So hexspec gives you a functional executable specification, but you may want to state more properties. You could imagine writing the summing all the odd elements as a function. Then you have an executable specification, but then you may give a shorter answer of what this sum actually computes. Was there a question? Yeah, someone's happy in the chat. That's very good. And what we hope to do is to further integrate with Crusoe to have both interactive and automatic checking in hexspec. And this is work together, or mostly by Blased. So this is a part about high assurance cryptography, and as I said, so we're also using this for smart contracts. So what are smart contracts? Smart contracts, there are many ways of thinking about this, but they're basically small programs running on the blockchain, and they can be used to automate simple banking tasks. For example, distributed finance, and you would have the tokens, all kinds of token standards. You would have a distributed exchange, an escrow. You could do voting, and this could be cryptographically secure voting. You can do all those things on chain, and the nice thing is that you're actually removing the middleman from many of these from many of these applications. Now this seems very nice, but as I said, so each week or a couple of weeks, someone takes out tens of millions of dollars that they shouldn't do. And so here's an example. If you look at the the stock of the D-Force distributed exchange. There was a small bug in the program, and someone took out some 20 million. Part of this is that these contracts are written in a legacy, basically JavaScript language, and already after the first accidents happened with this language, the Ethereum developers said, "Well, we need a better language for writing smart contracts." But so far, this hasn't really materialized on Ethereum. There's also the famous DAO hack. So DAO is a distributed autonomous organization, or a distributed funding agency, if you want. That was one of the first enormous hacks in the space. Now, what you can do, what is typically missing is people write a smart contract, but they don't actually write a specification of what should happen. So now we looked at a variant of this Uniswap, which was hacked, and then the specification we wrote is that no coins are lost in the process. So at each moment in time, the total sum of the amount of coins stays the same. And what we then did was we used our verification framework called Consort for contract certified to write to test to do property-based testing. And property-based testing we did was to actually look at traces. So we automatically generated traces of transactions, and then within 10 minutes, our property-based testing framework actually found that there was a trace where this contract was actually vulnerable. And so this can be done for many of these contracts. And I mean, as formal methods people, we know that just by writing the specification, often you already find bugs in your code. And so smart contracts are a good application for these formal methods. So why am I talking about smart contracts at a Rust formal methods group? Well, this is because the Concordium blockchain and a number of other projects, they're using Rust for smart contracts. So why is this? Well, one is Rust is a very nice language, which is fairly easy to understand, at least the subparts of this. But the other important thing is that one would like to have WebAssembly on chain. WebAssembly is a much better specified language, as I said in the beginning, than the EVM. Xavier, you have a message?
Yeah. So I just wanted to let you know that there's a question in the chat from Danielle Schwartz-Bone, who is asking, do we know what kinds of tools and techniques the attackers are using to find exploitable bugs?
My impression is that they just read the code and then abuse their understanding of the code. There are a number of tools to actually look for these vulnerabilities. So one of the things that happened in the DAO was that there was a reentrancy, and this was allowed to this allowed one to steal a lot of money from the DAO. There are now standard tools to look for reentrancy, and reentrancy is actually needed in the DAO. So by itself, it's not you shouldn't forbid it, but it's often a sign that there's something that could go wrong. So you could use tools like this to actually look for vulnerabilities. And so but typically these tools are just used to find anti-patterns. And of course, if you're using one of these tools to analyze smart contracts, if you find such an anti-pattern, that could give you a hint of where to find these bugs. So if you're using these methods, I mean, this may allow you to take out some money.
Yeah. So just a follow-up from me.
I don't recommend this because it's not clear that this is legal, obviously.
Yeah. So I have a little follow-up. So from what I'm understanding here, you're saying that primarily there are linters to help find these kinds of things, but there may not really be many model checkers or abstract interpretation based tools to really formally
It's
prove the
often
existence of
static
transits.
analysis.
Okay.
Yeah. Yes, as I said, so there's Concordium and a number of other projects. They're using WebAssembly on chain, and Rust, of course, is a very convenient language to actually generate WebAssembly because there's no garbage collector for Rust, and there's no garbage collector on WebAssembly. At least there has been a long-standing project to actually extend WebAssembly with a garbage collector, but it hasn't appeared yet. And even if there was, it wouldn't be clear that that's what you would like on a blockchain. Just a few words on what the Concordium project is. It's a proof of stake blockchain. So it's a green one, so it doesn't burn the planet like some of the other. So like Bitcoin, it has finality. It has identity, so that your transactions are private but not anonymous, and it's regulation compliant. And you can read more on the website. So the Consort tool, it's a mathematical model of smart contracts, and especially of interacting smart contracts. So we look at a smart contract as a pure program in the state monad, or just a pure program that actually transforms state. And we've modeled many of the standard smart contracts, so the DAO, escrow, token standards, decentralized exchange. And then we prove them to be functionally correct, and we do this by using the rich language of Coq, so we can write them in a dependently typed language. And then there's a standard way of translating any program in Coq towards OCaml or Haskell, and we've actually done this in a completely verified way using the MetaCoq system. So the standard extraction or translation from Coq to OCaml is unverified, but what we've done is a completely verified translation from a very rich fragment of Coq to just a simple lambda calculus. And then at the end, what one does is to print this lambda calculus to Rust. And then, of course, one needs to be a bit careful because Rust by itself is not a functional language, but of course it has a very clear pure part. And what we do is use the arenas in Rust to actually allocate all the memory in the beginning of the run of your program, and then once your smart contract ends, all the memory is freed again. So this is actually for smart contracts, this is a pretty good model. You had another question?
Yes, just about the use of arenas here. If you're allocating, you say you allocate all the memory at the start of a program. Are you able to place a bound on them? Are you then able to place a bound on the memory consumption of your smart contract, or how do you determine how much memory you need to allocate?
You allocate 46K in the beginning, and that's what you have to play with. So if you run out, then that's your problem. Yeah.
All right. Okay.
Now, this is of course very nice to. So if you're an expert in type theory, then of course you want to write your programs directly in type theory and generate some lower level code later on. But if you're an expert writing smart contracts and you're an expert Rust programmer, then you may want to start from Rust. So there's this very nice paper, Meeting Developers Where They Are. So this is also something that we started to do. So we start from Rust because the Rust language by itself, so you can do things like print hello world, and then the blockchain wouldn't know what to do with this. So we started to actually cut down the language and make sure that we have precisely the language we need for smart contracts. So we're building a dedicated sub-language to capture common smart contracts. And then we can embed this from Rust into COC, and this would be an embedding much like what we have for Hexpack. One thing I would like to do is actually also connect this up with the Crusoe tool to actually automatically prove things about smart contracts. Now, finally, a plug of more about cryptographic software, also because this is important for smart contracts. So smart contracts, smart contract language like Solidity comes with a dedicated library of cryptographic primitives. There are only a few, but in Rust you can just program your cryptographic implementations by hand, and then you use those. It's very important that you actually implement those correctly. The SSProof library is a library in COC that has features much like the EasyCrypt system. So it allows you to prove cryptographic security of certain protocols or cryptographic primitives. And one of the things we're doing is to make a connection with Hexpack so that we can actually prove cryptographic security of all kinds of cryptographic primitives or protocols. The interesting thing about this is that this methodology, the state separating proofs, is something that comes from the Everest project that tries to prove the TLS protocol to be secure. And this is a methodology that is used to write modular proofs, so you can actually attack bigger protocols. And in the same way, we hope to also hope to use this for bigger protocols to prove them secure inside the COC system. And we've already done this for parts of the TLS implementation, the ChemDem. This is just a small part, but it's still a substantial protocol. But we also did Sigma protocols, for example, which are used in zero-knowledge proofs. So again, as I said, we want to connect this, or we're in the process of connecting this to the Rust language. So just to wrap up, we can go in Rust from a specification to an efficient implementation in Rust. We were working a lot on high assurance cryptography in Rust, but we're also using Rust for verified smart contracts. So I hope that this gives some overview of the kind of work we're doing in my group and why this is actually relevant for the if you're working on blockchains. So thank you for your attention.
Thank you, Bas. I'm going to take some questions now. If anyone wants to switch on their camera, come onto camera, they can then ask the question. If you keep your camera on, you can make a follow-up point, and then we'll also scan the chat as well for people who don't want to come on camera and still want to ask a question. Please go ahead.
Oh, sorry, I'll let Alexander go.
Hi, thanks a lot for the talk. This is super interesting. Can you hear me okay?
Yes, we hear you great.
I can hear you.
Great, thanks. I was wondering, so you mentioned, I'm not sure if I got this part right, but you mentioned that you do the allocation in the Rust program using arenas, like Xavier was also asking. So does that mean that the data structures that you use in the program, is there any usage of the Rust type system itself, or is everything kind of, I guess I'm wondering, do you use the ownership in Rust at all to kind of constrain what the program can potentially do?
So I don't. There's no heavy use of the ownership.
Okay. I guess the reason I was asking, maybe this is not necessary because you can control in a sense what people can write, but the reason I was asking is, so we did this work that plugged in the chat about Ethereum contracts, about so the other Viper with a Y language construct. And one of the properties of the language that was very useful there compared to a general purpose programming language is that you can't give out references to your own data. So all the data stored in the contract is very strongly encapsulated compared to whether if you implemented this by hand in C++, or to some extent Rust, right? Even in Rust, if you could write arbitrary code, I guess you could hand out references of different kinds that would allow, in principle, others to mutate your data, and then that would make the reasoning we could do in the presence of maybe untrusted participants weaker still, let's say. So I'm wondering, do you get the same kind of encapsulation in this restricted Rust?
Yeah, I think so. I would need, we haven't proved anything particular about the subset we're targeting. But it's it's sort of like a folklore way of writing functional code in Rust using these arenas. So we're only using a fairly small fragment of Rust that we're targeting, which also means that maybe it's not the most idiomatic Rust you would write. On the other hand, we've looked at how big the code is and how fast it runs, and it's all it seems fairly reasonable.
Cool, thank you.
But yeah, I'd be very curious to know more about the current status of Viper. I noticed.
Yeah.
So you mean the Viper language or the Viper tool?
Well, it's confusing. So there are two Vipers, right? So there's Viper with a Y, which is this this Ethereum programming language, and then I mean there's a tool that we made that maps this down to Viper with an I, the verification language that we use. But I guess maybe what's more interesting for the sake of this discussion is the methodology involved there. So I sent the link in the chat in case you're interested, but the thing that I mean there it's not using this functional encoding. I guess we were looking at properties of the imperative language as an imperative language. But the thing that makes at the boundaries when you call out to someone else, in principle, because of callbacks, that can have somewhat arbitrary effects, but they're not completely arbitrary because of this encapsulation you have at the language level. So what you know is that at most, the callbacks can possibly call some sequence of the functions that we have written in the same file as where the state is. Whereas, of course, if we were in Java or something like this would be less clear, right? We could be handing out aliases, and of course, it could be causing all kinds of mutations. In a sense, then we'd have to throw all information away. And that difference, at least for the work we were doing in that paper, that difference was already pretty useful, that this encapsulation gives you a handle at least on the worst possible thing that the outside world could do to your state, I guess.
Yeah. So we certainly do have some encapsulation, but I haven't tried to bring it out. But that's a very good question. So we'll try to do that.
Cool. Thanks.
Thank you, Alex. Daniel, would you like to go next? Great to have you.
I was on mute, sorry.
No.
Yeah, so I'm curious about the sort of the overhead of this, both in terms of performance, but more importantly in terms of sort of size of code versus size of spec, amount of time it takes you to write, amount of time it takes you to modify, and sort of how usable do you think this would be for an average blockchain engineer, and how do we get it to the point where this is the default standard for something like blockchain?
So that's a very good question. So at the moment, what we can do. So this has been very hard work by some very clever PhD students, guided by an expert in type theory and an expert in cryptographic engineering. But then of course you only need to write such an implementation of for example BLS. You only need to write it once, and then you can actually print it to a number of languages. For smart contract verification, I think so. So currently, writing it in Coq, you really need to have expertise in writing this code in Coq. Some of these things are written by very clever master students or beginning PhD students. So that's certainly feasible with some training, but certainly not the average smart contracts writer. And that's why we're looking more into a small dedicated language that we want to embed into Coq, like somewhat in the spirit of Hexpack. And I would also like to connect to the Crusoe tool, which gives you some automated proving. So the convenience is certainly something that we need to work on. On the other hand, the testing framework that we have at the moment, so the testing framework is something we've implemented inside the Coq system, and it's just property-based testing, which is also available for Rust. So actually we have a project out for some clever bachelor students. So I hope to have some bachelor students next semester that actually want to implement this directly in Rust, and that should be feasible. It shouldn't be too hard.
And how have you found software maintenance? Like, so if you have to make a change to something that you've verified, how hard has it been to make the change and then corresponding proof changes?
So for smart contracts, I mean, we've written everything in Coq, so it's a usual maintenance. So you're just inside the system that you're using all the time, and then it's not too hard to do the maintenance. I think it will become harder if we actually, or slightly harder, if we're actually going to start from code in Rust and then need to keep both the generated codes in sync with the proofs. We're hoping to use Git for this and see that works, but that's something we need to experiment with. But those are very good questions that we're working on, and we're aware that they're hard questions.
Thanks.
Great. We have a question from Vitutas in the chat. How is a subset different from no stud or no standard?
How is a subset different from?
From no stud or no standard, no standard. Same thing that's used in embedded.
So say again, different.
How is a stand? Yeah, no STD. How is a subset different from no standard?
Oh, so what I have in mind is something of the form of Hexpack, which has its own small standard library and a very restricted subset. And the restricted subset is chosen in such a way that it's basically pure programming with states. So that's the way it can be translated. So the Hexpack language is really chosen in such a way that it has precisely what you need to specify cryptographic code, but you don't have any printing, you don't have any input from your keyboard or anything like that.
Right. Xavier, did you want to come in now with your points?
Yes, I had a final question, which might be a little bit provocative, but why Rust? I mean, you mentioned that you want to compile to WASM, but there are other languages that compile to WASM. And it seems like in a lot of ways, what you really want is a pure functional language in which you can control effects, because as you mentioned, you don't want to allow print, to print hello world in your smart contracts because that doesn't have meaningful semantics. But Rust has no functionality to really allow you to control that kind of effect. But maybe something like Haskell would be a better suited host language.
So we have in concert, we can also print to a functional language. One of the things we have on our to-do list is so there's a verified compiler toolchain inside inside COC, which is very much inspired and partially written by the same people that wrote the OCaml compiler. To actually, so this is the 30COC project. So one of the sub-languages, it's called Lambda ANF, which is an A normal form. And this is something that could be printed directly to WebAssembly. So this would be an alternative. And we can also print to other functional languages. The advantage of Rust is that you have more control over, you're sort of closer to the hardware, or at least closer to WebAssembly. So you can hope to write more efficient programs. And this is important because the efficiency here, both in storage, but also in running time, is something you're actually paying for. And you, especially when smart contracts become a bit bigger, this becomes a real factor.
Okay, so
so I think it's those two things. So it's a decent language that compiles very nicely to WebAssembly, but it gives you the control to write very efficient programs, and this is something that you actually pay for on the blockchain.
Yeah, and if you could just clarify one small point. From what I understand, you're saying, you also seem to say that you're printing meaningfully different code in Rust versus Lambda ANF. Like the Rust code you're going to generate is going to allow for better compilation by Rust than the Lambda ANF compiler would? Or are you just printing Lambda like functional code just in a Rust syntax and hoping the Rust compiler?
Well, we're printing functional code to Rust.
Okay.
So I think the code would be fairly similar.
Okay.
The advantage of printing to Rust is that you can probably more easily inspect it and tie it up to other smart contracts, for instance.
Okay.
But that would be an alternative route. But as I said, so we're also building a toolchain from Rust to COC, which should connect up with the rest of the toolchain. So the interaction, for instance, for the smart contracts, so that layer should still work as before.
Okay, well, thank you very much.